In this section, we'll look at a way of modeling matching problems with graphs. Let's go back to the class scheduling problem from the last section. You remember that we tried to solve this matching problem by finding a special tuple where each entry of the tuple was distinct. And if you remember, we created sets for each course. For course number 1, we created a set of letters A, C, and F. Set number 2, we constructed a set number 2 with the letters C, D, E, and G, and so forth. And a tuple was made of entries where each entry belonged to each set. This special tuple was called a system of distinct representatives. If we're able to find a system of distinct representatives, that means that we're able to solve the matching problem. In other words, we would have a letter assigned to each course that was different from the other ones. So this guaranteed that we had a professor assigned to only one course and one course to only one professor. If you remember, we were not able to find an SDR for this particular problem. So in this section, we're going to model this matching problem with graphs. And in this way, remember that this doesn't have a solution. The matching problem doesn't have a solution, but we can ask the question, okay, if we're not able to match a professor to each course, is there a way to find some type of solution that will give us the maximum number of courses that are assigned to professors? Also, another remark is that previously we were able to model the problem by creating sets, a set for each course, but we can also create sets for each professor. For each professor, let's say set A would have specific courses that that Professor A would be able to teach. So we could have done that too. So this demonstrates or highlights a symmetry with this type of graph. And the symmetry is better displayed if we draw the graph. As you can see here, Professor Abel, is available to teach course number 1, 3, and 4. And so this graph demonstrates that those possibilities. Now the matching problem is solved if we're able to find a specific set of edges that will connect one vertex from here to another vertex from this group. In fact, every time we're able to separate the vertices of a graph into two groups, where there is no vertices in one group, there is no edges between any two vertices, and the other group, there is no edges between any vertices. So if we're able to split the set of vertices into two, then we can call the graph a bipartite graph. So that's actually the definition right here. A graph is bipartite when its vertices can be described as the union of two disjoint sets, set of vertices 1 and set of vertices 2, such that each edge in the graph joins a vertex in V1 with a vertex in V2. So we could not have an edge joining two vertices within V1 or two vertices within V2. If there is an edge in the graph, the edge will join a vertex from V1 to V2. So that's the definition of a bipartite graph. And in the matching problem, we want to pair up courses and professors, which means that we want to find a subset of edges of the graph that will give us that assignment. Now, this special set of edges has to obey this specific property that no vertex in the graph can be incident with more than one edge of this special set of edges. That set of edges is called a matching of the graph. So this is a definition. A matching is a set of edges where no vertex in the graph is incident with more than one edge of this set of edges. So for example, if I go back here, let's say for example, we choose this edge here from 1 to A, and let's pick another edge, for example, 5 to B, and well, let's say we selected only these two edges. These two edges together make a matching. Why it's a matching? Well, that's because it's a subset of edges of the graph, and no vertex in the graph is incident with more than one edge. Let's say, for example, I pick this edge right here. Now I have three edges. Now these three edges they form a subset of edges, but it's not a matching. By definition, it's not a matching because see this vertex here? This vertex is incident with two edges of this matching or this potential or this subset of edges. And the reason that we don't want a vertex to be adjacent or incident to more than one edge is because we don't want to assign, as you can see here in this problem, we don't want to assign two professors to the same course, right? So that wouldn't be okay with our solution of finding a matching. A matching would be assigning a vertex here to only one vertex here on this side of the graph. So those three edges would not make a matching. Now I can have more edges. For example, if I select this edge here, so those three edges, they form a matching. We can have one more edge. Those four edges form a matching. And then you probably can see now what we want to accomplish. We want to find a matching that has the most number of edges. So far I have four edges. So it's a matching. I was able to find a matching with four edges. Here is one more edge I can select. Now I have a matching with five edges. Question, can I find one more edge? It looks like we're not able to find any more edges because if I, for example, if I select a 4 with A, then A would be incident with two edges, so that wouldn't be a matching. So it looks like I found a matching with five edges, and that looks like that's the most number of edges I can find. Okay. Okay, now that was a definition of a matching. A matching is a set of edges from the edges of the graph, where no vertex in the graph is incident with more than one edge of that subset. And then here's another definition. It's called a maximum matching. A maximum matching is a matching with the most number of edges that you can find for a specific graph. Let's take a look at these three examples. Well, it's the same graph, but I repeated three times so we can take a look at the different matchings. So here's a matching. It's a matching with three edges. Now, if I want to add an edge here, I wouldn't be able to because see here, if I cannot add any more edges to 1, 2, or 3 because I already have these three edges. And from 4, I would have to select either 4C or 4D, and none of those can be added. It looks like I have the most number of edges here, but then we cannot conclude that this is a maximum matching. So it's a matching with three edges, we cannot say that that's the maximum. So we have to investigate and make sure that there's no other matching that is a little different than this one that will have more edges. Look at this one. This is a matching, and it has 4 edges. So we found a matching that has more edges than this one here. Here's another matching. It also has 4 edges. So it looks like we have we're able to find a maximum matching here. If you think about it, there's no way you can find a matching with 5 edges because we would need one more vertex here, right? So this is a maximum matching. Here is another maximum matching. That's why we call a maximum matching, because you could have more than one, but all of them would have 4 edges. All the maximum matchings for this particular problem would have 4 edges. Okay. One remark here is that the definition of matching does not specify that the graph be bipartite. We're working with bipartite graphs, graphs where you can have split the graph into 2 set of vertices, where there's no edges within between any 2 vertices within each of the 2 groups. However, the definition of matching can be applied to any graph as long as it satisfies the definition here. As you can see, matching is a set of edges, okay, when no vertex of the graph is incident with more than one edge of that set of edges. All right, let's now look at another way we can, another way we can model this. Instead of using diagrams, it would be much easier, well, later on, it will be easier to model this with a matrix. And here is the matrix that represents this graph. Now, this is not the adjacency matrix that we learned before. If you remember, adjacency matrix, you would have, because this graph has 8 vertices, you would need 8 columns and 8 rows. So it would be an 8 by 8 matrix. But because this graph is bipartite, then we can actually split the vertices in 2 groups, and because there is no edges within each group, then we can safely write this type of matrix. This will indicate the edges of the graph. Here there is one edge from 1 to A, there's one edge from 1 to B, there's no edges from 1 to C or 1 to D. Here there is no edges from 3 to A, there is one edge from 3 to C. Notice that there is no danger here of missing edges. For example, from, let's say if I have an edge from 2 to 3, then I couldn't express that edge using this matrix. Well, but that's fine because this matrix is only for bipartite. If we had an edge here, then this graph wouldn't be bipartite. So remember that this type of matrix here, first of all, it's not an adjacency matrix like we learned before. It's a different type of matrix, and it works only for bipartite graphs. Now, if we work with the matrix with this type of matrix, then we can also have some analogous definitions for matching and maximum matching. So a matching would be selecting some of these ones that you see here in the matrix. So I can select, for example, if I select this number 1, I'm actually selecting the edge 1A. Once I select an edge here, I cannot select any other edge within this row or within this column. Otherwise, it wouldn't be a matching. So we can define also what we call an independent set of entries of the matrix. So an independent set that's equivalent to a matching. Okay. No two entries are in the same line. So if we have this one selected, then we couldn't select the other one. Let's say we have this one selected, we cannot select this one, and we cannot select this one or that one. So in any line, we cannot select more than one number one. And a maximum independent set of ones would be a matching or independent set that has the most number of ones in there. So here's the corresponding matrices for these bipartite graphs. So this is a matching with three edges. Look at how this matching will be represented with matrices. It will be represented by these three asterisks. So notice that I'm selecting these three ones. Look at this matching with four edges. This is the representation, the matrix representation of that matching. So the matrix itself represents the entire graph, and the stars, the asterisks, represent the matching. Here's another matching, and here's the matrix representation of that matching. So the matching is represented by these stars. Here is another definition that will be related to matching. We define now a covering of a graph. A covering is a set of vertices. It's a set of vertices of the vertices of the graph, such that every edge is incident with at least one vertex of the covering. In other words, any edge of the graph needs to touch a vertex of this covering. For example, let's pick a set of vertices. I'll pick a vertex 1, B, and 4. Okay, so I'm selecting that 1, B, and 4. Question, is this set a covering of the graph? Well, it's a set of vertices, but does that satisfy this definition here of covering? Well, it does not, because every edge, any edge of the graph needs to touch a vertex of this covering, of this set here. Clearly, for example, this edge here is not touching any of these three vertices. So it's not a covering. Well, let's pick more let's pick more vertices then. If I pick all the vertices, then that's certainly a covering, right? So if I pick all of them, 1, 2, 3, 4, A, B, C, and D, that's certainly a covering. It's a set of vertices of the graph. It has all the vertices of the graph, and it certainly satisfies this definition. Every edge in the graph touches one of the vertices. Now, the question is, can I have a covering that has fewer edges? And that's going to be the purpose of using this definition. And we'll see how that's related to matching. Now, when we look at the word covering, we can think of a covering as covering all the edges. So we want to select vertices in such a way that we were going to make all the edges touch, each edge of the graph touch one of the vertices of that covering. So we can start by selecting vertices that will cover the most number of edges at that particular place. For example, if I select this vertex here, that will cover these two edges right here. So that takes care of those two edges. Notice that if I select vertex C, that takes care of these three edges right here, the 2C, 3C, and 4C edges. Um, then that leaves 2B, that's the edge that we're not covering yet, and 4D. Well, we can select D, and that takes care of these two edges right here, the 3D and 4D. And finally, this is the last edge that we need to cover. I can either select B or 2. If I select B, that takes care of this edge. So notice that the set of vertices 1, B, C, and D, that is a covering. And again, why it's a covering? That's because any edge of the graph, of the original graph, is touching or is incident with at least one vertex of this covering. So we were able to find a covering with only 4 vertices. Yeah, if we select all the vertices, then we are safe. That's certainly a covering. But the purpose here is to find a covering with the minimum number of vertices. Here's a question. Is it possible to find another covering for this graph that has 3 vertices instead of 4? If we're able to find that, then we need to keep going until we find the minimum number of vertices that you can have in a covering. Once you find the covering that has the minimum number of vertices, then that's called the minimum covering. So let's go back here, and that's the definition of a minimum covering. If no other covering has fewer vertices, that's called a minimum covering. So in the graph above, we saw that if we select all the vertices, that is a covering. And if I select the vertices 1, 2, B, 3, C, and 4, that is also a covering. It's a covering with 6 vertices. 1, 2, 3, 4. If I select all these 4 vertices, that's a covering, and it looks like it's a minimum covering. Here's another one, 1, 2, C, D. That's another minimum covering. And why it's a minimum covering? Because there is no covering with 3 elements. At this point, the only thing we can do is by really you know trial and error, and then do some analysis to see that there's no other covering that will have 3 elements. In fact, this is not very difficult. Um, if you have only 3 vertices, right? Any 3 vertices. If you look at any 3 vertices, you're always going to leave one edge out, because you can see here, um, right, that any subset of vertices, of 3 vertices, would always leave an edge out. Okay, now let's go back to the matrix, the bipartite matrix, and we can actually indicate a covering in the matrix by simply circling an entire line, either a column or a row. So a covering of a graph is a set of vertices such that every edge is incident with at least one vertex of the covering. That's the definition of covering. And converting that into a matrix format, a covering of ones is a set of lines containing all the ones of a matrix. So we circle either a line, a row, or a column, or both, in such a way that we'll cover all the ones that you see in the matrix. So for example, if I circle that row, then I'm covering these 2 edges. It's the same as selecting vertex 1. Vertex 1 will take care of these 2 edges here. And then I can I can circle row 2, row 3, row 4. So that is a covering. It is a covering because you're covering all the ones in the matrix. Remember when I said that selecting all the edges, all the vertices, that is also covering? Yes, here it is. Um, it's like shooting a fly with a cannon, right? You're selecting all the vertices, then you're certainly going to cover all the ones in the matrix. So that is the representation, the matrix representation of this covering. Now, if I do that, if I circle row 1, column B, column C, and column D, notice that all the ones in the matrix are covered, and that represents the set of vertices 1, B, C, and D. And that is a minimum covering. It's a covering with 4 vertices, 4 elements. Now, there is a theorem in this section that relates matching with covering. It's a very interesting relationship. The theorem says that if you have a matching, let's say you have a matching and you have a covering. Remember, matching is a set of edges and covering is a set of vertices. Now, those are special set of edges and special set of vertices, right? A matching, um, you cannot have um, a vertex of the graph that is incident with more than one edge in the matching. And a covering, every edge in the graph needs to touch one vertex of the covering. Now, if you have a match, any matching, any covering, the theorem is saying that the number of elements in the matching is less than or equal to the number of elements in the covering. In other words, the number of elements in the matching it's always is no more than the number of elements in the covering. That could be any matching in any covering. It's always like that. Now, also the theorem says that if you do have a matching with the same number of elements as the number of elements in the covering, then you've just found a maximum matching and a minimum covering. Now, let's say, just to illustrate, let's say if you found a matching that has 5 edges, and you found a covering that has 5 vertices, then that covering is a minimum covering, and that matching is a maximum matching. So if you have the equality in number of elements, then the theorem guarantees that that matching is a maximum matching and that covering is a minimum covering. Now, the general number of edges in the maximum matching is not necessarily equal to the number of vertices in the minimum covering. In other words, the converse of this statement here is not true. If I say, if you do have a maximum matching and a minimum covering, it doesn't mean that the number of elements of a matching is equal to the number of elements in the covering. Okay, so it's important to understand that. Um, it's like saying if it's raining, then the ground is wet. But the converse is not always true. If the ground is wet, it doesn't mean that it's raining, right? It could be someone that was using a hose to to wet the floor, the ground. So it's a conditional statement, and the converse is not always true. Now, however, if the graph is bipartite, then the converse is also true. Then a maximum matching has the same number of elements as a minimum covering. That's Koenig's theorem on page 340 in the textbook. Now, in the previous example, we were working with a bipartite graph. So we had a minimum covering, and because that was a minimum covering, a maximum matching will have 4 edges because this minimum covering has 4 vertices. Now let's go back to the class scheduling problem. Let's find a covering for that matrix representation. So this is the matrix representation of that original um, graph of courses and professors. So here is a covering. So 2, 5, A, C, and F. Notice that all the ones in the matrix are covered. So that is a covering. Now what does that mean? Well, because this is a bipartite graph, it says that a maximum matching will also have 5 edges. In other words, um, even though we have six courses and 7 professors, we're gonna able to find only a matching with 5 edges. That the matching that has the most number of edges will be matching with 5 edges.